Hello, we're going to work on sample size problems right now, and basically the question we're trying to answer here is, if I take a sample, how large does it have to be? And so we can abbreviate them, SS, I guess, sample size. So this kind of problem is relatively easy to recognize because the question will say something like, how large a sample do I need to take? So that tells you sample size problem. Now there are going to be two variations on the sample size problem, so we'll have to know which one is which, but as far as recognizing the basic type of problem, it shouldn't be too difficult for us. All right? Now before we can determine the answer to that question, how large a sample to take, there are three questions, that we need to answer. Three basic questions. And let me write those down for you. The first one is, what level of confidence do I want to have in, let's say I'm estimating the mean. That's what the first one will be. Sample size problem to estimate the mean. How confident do I want to be that the actual mean is going to be contained in the value that I come up with? How confident do I want to be there? So my confidence level is going to be 90%, 95, or 99, probably one of those. And if nothing else is given, I always assume 95%. If we give you something else, then use something else. So remember, my objective, the kind of problem we're talking about is, I'm trying to determine what size sample should I use to estimate the population mean. First thing I need to know is, how much confidence do you want in the answer that I give you? 90%, 95, or 99? How good an answer do you want? Second question is, how much error are we willing to live with? In other words, plus or minus what would be acceptable? Of course, we'd like no error, but in order to get no error, we'd have to increase the sample size so it was equal to the population. And that would be quite expensive, so we probably wouldn't be willing to do that. But plus or minus 2, plus or minus 5, how much error are we willing to live with when we estimate that population mean? All right, and thirdly, we want to know something about the population variance. Okay? How similar are the values in this population? The more similar they are, or the less variation or difference there is, the smaller the sample size can be. The greater the amount of variation, or the larger the standard deviation, the larger my sample size will need to be to have the same level of confidence and the same amount of error. So conceptually, let me talk a little bit about the relationship between these three issues right here. Ideally, we would like to have 100% confidence, no error, and little variance. But the only way to make sure we've got the right mean is going to be to do the whole population. We don't want to do that, so how does the trade-off process work? Other things equal, as we increase our level of confidence, from 90 to 95 to 99, the size of our sample is going to have to move up. Okay? To be more confident, we need a larger sample, a greater percentage of the total population will give us more confidence. Error. The greater the amount of error we're willing to live with, the smaller the sample size needs to be. If we want little error, we've got to have a larger sample. If there's lots of variation in the population, if we have a large standard deviation, we're going to have a larger sample size to maintain the same level of confidence and error than if we have less variation, in which case we can get by with a smaller sample. Okay, so those are the three basic questions. Now notice what question is not listed there. We don't have to know what the size of the population is. Now there is something called the finite population correction factor, which we could use if our sample size becomes too large relative to the population. But for the most part, the size of the population doesn't really matter. Only these three things matter in terms of deciding what size sample to use. Okay, so let's look at the formula then for the first kind of problem here. And we would say, here's the formula found on page 254 in the middle of the page. N, that's what I'm solving for, the sample size equals z squared times sigma squared over e squared. Okay? Z squared, this is going to correspond to my confidence level. Sigma squared is going to be question number 3, and E squared is going to be the amount of error that I'm willing to live with, plus or minus what. So all we need to do really is to plug numbers into our formula and solve for n. Now the easy place to make a mistake here is forgetting to square each of those values. So E is squared, sigma is squared, z is squared. If you don't square each of those, it will give you an incorrect result. Also, whenever you do a sample size problem, remember we always round up. Okay, that means if I came out with a value like 248.1, I would still round up to 249. You always round up to the next highest whole number because you want to maintain the level of confidence and the error given the amount of variation that exists in the population. So round up, otherwise I'll take 1 point off if you give me 248.1 because we can't have part of an observation. We either took that sample or we didn't. So it's got to be a whole number. So just round up to the next highest whole number. All right, let's try an example then of this kind of problem so we can see how it might work. We'll do one that's here in the chapter, and it is on page 255. We're going to have a sample. Okay, here's our question right in the middle of the page. After consultation with company officials, you determine a sampling error of no more than plus or minus $5. Okay, so I'm going to move my page down. And I'm going to say E equals plus or minus 5. That's what the problem told me. Okay, so I just wrote it down. E equals plus or minus 5 is desired along with 95% confidence. So I'm going to write that down. 95% confidence. Past data indicate that the standard deviation of the sales amount is approximately $25. So this is not based on a sample. This is what somebody told me. So I can say sigma equals 25. So now I'm ready to plug into my formula. Okay, the formula, remember, says n equals z squared times sigma squared over E squared. So E, we already know what that is. That's going to be 5 squared, 25. My numerator is going to be 2.5 squared. That's going to be my variance, which is the square of the standard deviation. Now notice, if they gave me the variance already, I wouldn't need to square it. But the value they gave me was actually the standard deviation. So that's why I'm having to square it. Okay, the other value I need is a value for z. Now I've got a 95% confidence level, and for any sample size problem or any confidence interval problem, I'm always going to assume a two-tailed test, which means if I have 95% confidence, that's in the middle, and therefore I'm going to have 5% out on the ends. That's going to be 0.025, 0.025 in each tail. You might be beginning to remember this value, but if not, you could go back to your table again and look it up, and you should find that since it's a z formula that I'm using, two-tailed problem, and the confidence level is 95%, you should end up with the value 1.96. Let me show you where I got that value from. Okay, I'm on page 552 again, and I'm going to look up the area, 0.025 in the middle of the table. We always find areas in the middle. 0.025 is right here. Okay, I go across to the left. I have 1.9. Go up to the top, 0.06. Remember, we use an absolute value over here. 1.9 plus 0.06 gives me 1.96. Okay, so my value that I'm going to plug into the formula would be 1.96. But remember, square it. Got to square each one of those values to find my sample size that's required. Okay, so let's go back to the page in the chapter. And we've got 1.96 squared times 25 squared over 5 squared. So if we multiply those numbers out, we get 96.04. That's my value for n. 96.04. Now what I want you to do is round that number up, remember, to 97. So what I can say is if I am trying to estimate the mean for a population, I want 95% confidence, my standard deviation equals 25, and I'm willing to live with plus or minus 5 as the amount of error in my answer, I can use a sample of size 97. It doesn't matter what the population size is, I still would have 95% confidence, and I'd be within plus or minus 5 if the standard deviation equals 25. All right? Now, let's give you a couple other hints here in case the kind of problem you need to work doesn't give you all that information. If you don't have the value for the population standard deviation, then you can use some other estimates. If it tells me sigma, use sigma. If it gives me the population variance, use the population variance. If I don't have either one, then what I'm going to have to use is S, which is the sample standard deviation or the sample variance. If the value came from a sample, then it's a sample value. If it was told to me to be true based on past experience or from the population, that would be sigma. Remember, they're not the same, so be careful when you read your problem, just like you did with Z or T. And the other possibility is, if we don't know sigma and we don't know S, our third choice is going to be to estimate the value for S based on the range divided by 6. Okay, the range is the largest minus smallest value in the population, and 6 is just a constant. So if I take the range and divide by 6, that's going to give me an estimate of S, which is an estimate of sigma. You're going to have knowledge of the range, the highest value and the smallest value. Then you could calculate the range and divide it by 6. So here's my first choice, second choice, third choice. Go with sigma if you know it. If not, go with S. And if you don't know either one, then use the range divided by 6. Incidentally, that last value there is not given in your text, so you might want to write that down just in case you would need to use it. Okay, let's practice one more problem here, and then we'll go on to the next kind of problem. This is problem 8.38 found on page 258. It says, a survey is planned to determine the mean. So we're trying to estimate the mean again, so that's important. Annual family medical expenses of employees of a large company. The management of the company wishes to be 95% confident. So we want to write that down so we don't forget. Let's go to a new sheet here. Whoops. That's not what I want. There we go. Okay, let's go to a new sheet, and we're going to write down 95% confidence. This is problem 838. Okay, back to the problem. That the sample mean is correct to within plus or minus 50 of the population mean. So that tells me that E equals plus or minus 50. A previous study indicates the standard deviation is approximately 400. Now that's a previous study. It wasn't based on a sample, so that value is sigma equals 400. Those are the three questions. So it looks like I'm pretty close to being in business here. How large a sample size is necessary if the management wants to be correct within plus or minus 25? What sample size is necessary? Okay, so we're going to work this problem then, and what we're going to do is use the formula that we just had. N equals Z squared times sigma squared over E squared. I'll just write it down again. Okay, sigma squared is, Z squared is 1.96. You're probably beginning to remember that value because we've used it so much. It's 95% confidence, and we always assume that the variation could be in either direction, so that's why we're using 2.5% of the area on each side. We have sigma as 400. It's squared, however, so make sure you remember to square it. And then we divide by E squared, which is 50 squared. So to find N, I've got to multiply all those and then divide, and I come up with, for this problem, 245.86. 86, that's 45. Okay, now remember, 245.86, I want to round up, So that's going to give me 246. So my answer to part A is I need a sample size of 246 observations to be 95% confident that my answer is within plus or minus 50, given that the standard deviation is 400. Now in part B, they want us to revise the numbers slightly. They want us to change one number is all. They want us to change e squared to 25 instead of 50. So everything else stays the same. So this is part B. That was part A up here. Okay, so in part B, I say n equals 1.96 squared times sigma squared, which is still 400 squared, over e squared. Instead of 50 squared, I now have 25 squared. Okay, so when I work those numbers out, it's kind of interesting how the answer comes out, because the result that I get now, instead of being 246, is 983.41. Which I can round up to 984. Okay, so notice what's happened here. We took our problem that we had before, and we changed only one number. We reduced by half the amount of error that we were willing to live with. Instead of plus or minus 50, we made it plus or minus 25. By reducing that value by half, the result is that our required sample size is now just about 4 times what it was before. 984 instead of 246. So the more precision you want, the less error you want, the greater the sample size has to be. And we can see that pretty clearly in the result of that problem. Okay, we have one other sample size problem that we need to talk about, and that is called the sample size problem for the proportion. So the difference is we're trying to estimate the population proportion rather than trying to estimate the population mean. The symbol for the proportion for the population, remember, is pi. Okay, so this is continuing in section 4 of chapter 8. The difference in this kind of problem and the one we just looked at is going to be the type of data. Here we have nominal data. As we mentioned before, nominal data just means that we're talking about frequencies or percentages. Okay, so if we look at a problem, we say, gee, no means, no standard deviations, it's not interval or ratio, so it must be nominal data. Our objective is the same as the last problem, however. We want to estimate what size sample to use if we're trying to come up with the population proportion. How large a sample do we need to estimate what the proportion would be? So the formula for this is slightly different from what we had before. It's found on page 256 toward the bottom of the page, and this is what it looks like. N is equal to, so we're still trying to find that sample size, n is equal to z squared, just like before. The denominator is still going to be e squared, but the only difference is going to be, here we're going to have pi times 1 minus pi. Okay? So, this is the amount of error, this is the confidence level, and this is the estimate of the amount of variation that exists in the population. So, first thing to notice is I've got to know this is nominal data. If I look at the data and there isn't any mean or standard deviation, then that's going to give me a pretty good indication of what we need to do. Let's use an example from the chapter, page 257, and then we'll work another problem. Middle of the page, returning to the Saxon Home Improvement Company using statistics scenario, suppose the auditing procedures require you to have 95% confidence. So I'm going to write that down. I think it's always helpful to write down what the problem gives you so you can kind of keep track of things a little bit. 95% confidence. In estimating the population proportion, there's a key word. That tells me I'm interested in the proportion now of sales invoices with errors to within plus or minus 0.07. Okay, so E is going to equal 0.07. Now really what that is 7%. But whenever I put it into the formula, put it in decimal form. 0.07 means 7%. Don't put 7 in there because that's going to give you the wrong result. It's just 7/100ths is what we're looking at there, or 7%. Okay, reading again in the problem. The results from past months indicate the largest proportion has been no more than 0.15. Okay, so they're telling me we think maybe the proportion might be about, proportion might be about 0.15. Okay, so that's the value they gave me. They think it might be 0.5, but we're going to use the sample size to kind of estimate whether that's really about right or not. Okay, so 0.15 goes into my formula. So I'm going to then take the information I'm given, plug into that formula, and solve for n. And that's how I find out my sample size. So z squared, z is based on 95% confidence. It's a z value. It's still, because it's a sample size problem, I still could have error in both directions. So it's just going to be 1.96 squared. Again, 1.96 squared. E squared, remember, is going to be 0.07 now, squared, and the proportion, I think, is 0.15. So I'm going to use that, and then 1 minus that would be 0.185. 0.85 times 0.15, multiply those, then multiply by 1.96 squared and divide by 0.07 squared. When I do all those operations, I'm going to end up with my answer, which is 99.96. So n equals 99.96. Remember, round up is going to give me 100. So my required sample size here is going to be exactly 100. If I want 95% confidence, I'm willing to live with 7% error, and the population proportion is equal to 0.15. Okay, now, here we had the advantage of knowing what the proportion was. It gave us that information. If it didn't give us that information, we'd have to use something else. So there's my first choice, pi. If I don't know pi, then I'm going to use the sample proportion, which is p. If it gives me the sample proportion, I would use that as my second choice. If I don't know either one, then my third choice is 0.50. Now this value I'm going to use because if I take 0.5 times 0.5, I get 0.25. That's the greatest product that I'm going to get given any possible value of p. So what I'm doing really is I'm assuming the worst case. If I don't have any idea, I'm going to assume it's 0.5, and that will allow me to make sure that I've got the right answer within 7%, 95% confidence, but it's going to require a larger sample size because my proportion is no longer 0.15, it's 0.50. So those are the three values. Use pi first, then p, then 0.5 if you don't have either of the other two values. Here, pi was 0.15, that's why I used it. Okay, now we are finished with Chapter 8.